for the day. Okay, so my usual timing will be 7 to 8 unless otherwise informed. Okay. I hope you hear me, right? Asif,
Yes, ma'am.
Yes,
somebody
ma'am.
please respond. Joshika. Okay. Okay, so we'll start. Probability distribution. And what we will discuss today is discrete probability distribution. Okay. Later we will move on to the continuous probability distribution. So what is a probability distribution? So far we have been talking about the simple probabilities, and then we introduced random variables, and then we introduced something called probability function, right? What is a probability function? If you remember, can somebody say? Okay, so probability function is something that assigns a value to each of the outcome of the experiment. Okay, so that's the probability function. Okay, and the probability distribution is a function that describes the likelihood of obtaining the possible values that the random variable can take. Okay, that is, you have there is an experiment and there is a list of possible outcomes and how likely it is to get a particular outcome. Okay, so that is the how likely is called the likelihood of obtaining a possible value. Okay, you assume some value. What is the probability that this value could occur as the output of this experiment, okay, or this trial? Okay, so that is what is being described by the probability distribution. Okay, so in other words, you can say the values of the variable vary based on the underlying probability distribution. Okay, that is, if you assume different probability distribution for a particular random variable, okay, the likelihood of obtaining that outcome will vary. Yes or no? So this will be more clear when we go and discuss different distributions. Okay, but keep this in mind. Okay, so if the underlying probability distribution varies, then the probability of obtaining a particular output will also vary. Okay, so so this is the first discrete probability distribution that we are going to see. A simple but important one. Okay, Bernoulli distribution. Okay, what is its role? It models one trial in an experiment that can result in either success or failure. Okay, so how many outcomes are there in this experiment? Can anyone say? How many outcomes are there?
Ma'am, 2, ma'am.
Am I connected or not?
Yes, ma'am.
Am I with you?
Yes, ma'am. Audible, ma'am.
Yes, ma'am.
Ma'am? Ma'am?
Okay, I think I was in mute all this time, right? And you, oh,
Yes,
sorry.
ma'am.
See, you guys has to respond me little earlier, okay? Mm, okay, once again. Okay, so as already said, okay, there are two outcomes of the experiment. Okay, one is the success, the other is the failure. Okay, and the Bernoulli distribution models only one trial. Okay, so the one trial could result either in success or failure. Okay, so we say that a random variable x has a Bernoulli distribution with the parameter p if x takes the value 0 and 1. Okay, the possible values are 0 and 1, and at a time x can take any one of these values. Okay, and 0 represents failure and 1 represents the success. Okay, and the probability of the random variable x getting the value 1 is represented by p, and probability that x will take the value 0 is 1 minus p. Okay, and we write the Bernoulli distribution using these notations. Okay, x tilde Bernoulli of p means x is a random variable that follows the Bernoulli distribution with parameter p. Okay, same as Ber p. Okay, both represents the same thing. Okay, so we say that x follows a Bernoulli distribution with the parameter p, or we can also say that x is drawn from a Bernoulli distribution with a parameter p. Okay, what do you mean by drawn from a Bernoulli distribution? Can anyone say? See, both mean the same. Okay, x follows a Bernoulli distribution with parameter p, and x is drawn from a Bernoulli distribution with parameter p. Both are same, but can you see say what do you mean by drawn? Okay, so drawn means actually we are generating the samples. Okay, samples that follow this distribution. Okay, so this is from the point of generation, and this is from the point of constructing the distribution. Okay. Okay, so this is Bernoulli of 1 by 2. Okay, what do you mean by 1 by 2? P takes the value 1 by 2. That is, the probability of the success is 1 by 2. Okay, and what will be the probability of failure then? So probability of failure is also 1 by 2. Probability of success is also 1 by 2. Because probability of failure you will get by 1 minus p, which is 1 by 1 minus 1 by 2. So you will get 1 by 2. Okay, and this is the cumulative distributive function. Okay, and you have the possible values a along the x-axis, and this is p of a. Okay, the probability mass function. So you have half, around the half you have the value for 0 and 1. Okay, and the cumulative distribution, it starts from 0, and for 0 you have the probability 1 by 2. Okay, and the cumulative probability will be reaching 1 when you have the value 1, because you have only two samples, right? 0 and 1. And it's not samples. Okay, two outcomes. Okay, so if in general, if you have a p here, okay, this half will be replaced by what? P. Okay, and you have the failure, which is 1 minus p. Okay, and here we have p, and this is do you have any idea, is this correct? 1 minus p here and 1 here. Is this diagram correct? Is this always true, this order of listing the values? Anyone? Do you understand my question? Okay, in the graph it says I have 1 minus p and then p and then we have 1. Is this true? This listing always true? Is this always true? This order of listing, I'm asking about the order of listing in the axis, in the y-axis. Padmini? Is this listing of 1 correct? Will this be above p and 1 minus p? Okay, so this should be correct, right? So 1 should be above this 1 minus p or p, okay? But this listing, okay, among p and 1 minus p, okay, anything can come before this one. Suppose if p is, say, uh, 0.7, okay, if p is 0.7, then this is okay. This will be 0.3 and this is 0.7 and this is 1. Suppose if p is 0.3, then 1 minus p will be 0.7. Okay, in that case you will have p here, 1 minus p here and then 1. Okay, so it's not always that 1 minus p has to be less than p. Not. It's not like that. Okay. So in this example, we assume that okay p is much greater than 1 minus p. Okay, so that's why they have given p minus 1 minus p is a lower value and then p relatively a higher value. Okay, and the cumulative distribution as usual it reaches 1. Okay, any doubt so far?
No, ma'am.
Okay, so we'll extend this and extend this to n trials, okay, which is the binomial distribution. Okay, Bernoulli distribution models one trial and we are going to do n such experiments and that is being modeled by binomial distribution. Okay, again this is a discrete probability distribution. Okay, so you have n trials and each trial has a success with probability p. Okay, that is what is indicated by binomial of n comma p or bin of n comma p. Okay, models the number of successes in n independent Bernoulli trials. Okay, the Bernoulli p trials. Okay, Bernoulli parameter p trials. So it models the number of successes. Okay, and the number of trials is n. The sample space of the binomial trial will be what? The sequence of heads and tails of length n. If I am taking n trials, if you enumerate the individual outcome of the experiment, okay, each trial has n experiment, right? So you will have n output that will represent a single output of this Bernoulli. Right or not? Okay, so that's why we say it is a sequence of heads and tails. Heads and tails mean to say that it is success and failure. Either you can write it as 1 and 0 or head and tail. Okay, but the length of each outcome is length n. Okay, the question is now what is Bernoulli of 1 comma p equal to? Can anyone guess? I repeat, Bernoulli of P models one trial, okay, with probability of success as P and probability of failure as 1 minus P. And binomial distribution models number of successes in n independent Bernoulli of P trials. Okay, that is, this Bernoulli is repeated for n times. Okay, that is the meaning of binomial of n comma p. Now, what will be binomial of 1 comma p equal to? What is the value of n here in the question? What is the value of n?
1, ma'am.
1, ma'am.
What happened? Everybody has 1, right? Yes. So if it is 1, what will be equal to?
1.
Instead of n independent trial, I have only one trial. That means what?
மேம் பி ஆஃப் ஏல 1 இருக்கு இல்லைங்க மேம், அது மட்டும் வரும் மேம்.
It will be equal to Bernoulli of P, right?
எஸ் மேம்.
Because Bernoulli of P means I am just making one trial with the probability P to be success. Okay, and if I repeat this Bernoulli experiment for n number of times, ஏதம்மா? ஒரு பெர்னாலி ட்ரையலுக்கு ஈக்குவல் ஆகுமா இல்லையா? Instead of n, one trial. Okay, so that is equal to Bernoulli of P. Okay, so given by this one. Okay, so the values of A can be 0, 1, 2, 3, etc. up to n. Okay, because we are making n different trials. Okay, so 0 means what? No success by the Bernoulli distribution. Okay, and since we are repeating it for n number of times, okay, we'll get the power n. Okay, and if you have the value 1, that means that we have 1 success and n minus 1 failure. Okay, so we have n chose 1. The probability of success is p, so it is p power 1, and n minus 1 trials are failure, so you have 1 minus p to the power n minus 1. Okay, if it is 2, there are 2 success and n minus 2 failure. What is the probability of 3 or more heads in 5 tosses of a fair coin? Okay, this we can list out and get also. Okay, but we will use this binomial coefficients and compute. Okay, the binomial coefficient associated with n is equal to 5 or n choose 0 is, okay, so this is 5C0. Okay, which is 1, and 5C1 is 5 factorial divided by 1 factorial into 4 factorial. So you'll get 5. If I choose 2 is 10. If I choose 3 is 10. Okay. And if I choose 4 is 5. If I choose 5 is 1. Okay. Can you see a pattern here? Okay, the extremes we have got both are 1. Okay, and the second one and the last but one have the same value. The middle ones have the same value. Okay, so it's, do you see this pattern? Okay, so it's like 1 5 10 10 5 1.
Ma'am,
It's kind of, yeah.
ma'am, screen is not visible, ma'am.
Yes, but
Ma'am,
visible.
PPT is not.
Minute. So hope it is okay now.
Yes, ma'am.
Okay, so
Okay.
okay, so the binomial coefficients, if you see, okay, you have a pattern. Okay, this is the first coefficient and this is the last coefficient, and they take the same value. The second coefficient and the last but one coefficient, they will also take the same value. Okay, similarly, so it is kind of a symmetric one. Okay, and how do you compute the probability of 3 or more heads in 5 tosses? Okay, so we want P of x taking 3 or greater. Okay, so x greater than or equal to 3 is what we are interested in. Okay, so we can compute directly by substituting this one. Okay, so this is, so we have just substituted the binomial coefficients. Okay, so for 0 we have 1. This is the n choose 1, which is 5 choose 1. This is 5 choose 2, 5 choose 3, 5 choose 4, and this 1 will be again 5 choose 5. Okay, so we have to just add these 3 probabilities. Okay, so we have to just add these 3 probabilities, okay, to get the result. Okay, and we know that, okay, so we are told that P is equal to 1 by 2. Are we told this P is equal to 1 by 2 anywhere? In the problem, are we told that P is equal to 1 by 2 anywhere? We fix k is equal to 2. Okay, n is the number of trials and k is the number of successes. Okay, so we fix the number of success to be 2. Okay, so how to, and we are going to repeat the same problem. Okay, so we are trying to find what is the probability of getting exactly 2 success out of 5 trials. Okay, so when you flip the coin for 5 times and you need to get exactly 2 heads. Okay, we assume that the success is a head. So these are the 10 different listings. Okay, so we can list out all these 10. Okay, and we know
Ma'am,
that the number of, two heads, number of two. Yeah,
Ma'am, again PPT is not
Padmini,
visible. Again PPT is not
any
visible,
problem?
ma'am. Yes, ma'am.
But is that my connection is poor? Okay, maybe I'll keep this. Okay, so that I know if my PPT is going off. Okay. So we can list out all the 10 outcomes which will have exactly two heads. Okay, and we can find the probability of this one. Okay, what will be the probability of getting exactly two heads out of five coin flips? I mean, it should be at your tips now. What is the probability that we get exactly two heads in a five coin flips? What is the size of the sample space? Come on. What is the size of the sample space? You have five coin flips, okay? So you need to have a length of five, all the strings with length five. So it is 2 to the power 5, which is 32, right? So that is the size of the sample space, and the number of samples which is getting exactly two heads are listed here. Okay, you have 10 such samples, so it is 10 by 32 is the answer. Fine.
Yes, ma'am.
Excuse me for a minute, okay? I'll change my mobile, okay? My connection is very poor and it is often disconnecting, okay? Just hold on for 2 minutes. So, what we are trying to say is we have listed out 10 outcomes which will have exactly two heads. Okay. And we say that each of that output is equally likely. That is, it has the same probability of occurrence. Okay. Why? Because the coin is fair and each of the experiment is independent. Okay. Each of the trial is independent. Okay. So we have the same probability of occurrence for every entry. Okay. And each entry will have two success and three failures. Okay. Which can be modeled by this one. Okay. P square into 1 minus P, the whole cube. Okay. Why this is possible? Because the trials are independent. Okay. That's why I'm able to multiply the probabilities of independent trials. Okay. And the total probability of exactly two heads will be, we have to add this for 10 times, right? We have to sum all the 10 identical probabilities. Okay, so I have to add this for 10 times, which is nothing but 10 into this one, which is nothing but 5 choose 2 p square into 1 minus p the whole cube. Okay, so that's why this coefficient appears. I hope you will appreciate this, right? Is this clear? Any response? Yes or no?
Yes, ma'am.
Okay, fine. Okay, so next one is the uniform distribution. So this models any situation where all the outcomes are equally likely. Okay, you can have any number of outcomes, and again this is discrete distribution. Okay, discrete probability distribution. We say that the random variable x is modeled with uniform distribution with n, mean to say that x can take values from 1 to 3 etc up to n. Okay, and the probability of occurrence of each of this output is 1 by n. Okay, very simple distribution. And wherever we have this condition, okay, all outcomes are equally likely, no bias. Okay, in that case you can go for uniform distribution. Okay, so I think I'm reaching almost the end. Okay, so next is the expect. So before we go to the next distribution, okay, I wanted you to know these things. Okay, expected value, and one more concept, which is the deviation. Okay, so what is expected value? Okay, suppose we have a six-sided die marked with 5 3s, okay, and 1 6. Okay, what would you expect the average of 6,000 rolls to be? You have a die, it has 6 sides. Okay, and out of 6 sides, 3 sides have 3. Sorry, out of 6, 5 sides have 3. Okay, and only one side has the value 6. Okay, and you are rolling this die for 6,000 times. Okay, and you wanted to know the average value out of this 6,000 rolls. So we cannot, independently roll the die for 6,000 times and note down what value we have got, and we cannot find the average. Okay, that is highly impractical. Okay, this is where your probability distribution comes in. Okay, see here again, this I can model with what? Can you see that I have only two outcomes? Okay, one is 3, the other is 6. Okay, so whenever I have two outcomes, I can think of what? The Bernoulli distribution. Okay, I can assume one as success, the other as failure. Okay, so I can expect roughly 5 by 6 times 3 and 1 by 6 times 6. Okay, so this is using the simple Bernoulli. You can, I mean, out of since there are 6 sides, okay, approximately when we roll it for 6 times, 5 times it could have the 3, and one time it could have the 6. Okay, so assuming that, so this is where this is a rough estimation. Okay, assuming that this is true, okay, we just get the expected count. Okay, so out of 6,000, so 5 by 6 into 6,000. Okay, so that's how we get this 5,000, and 1 by 6 into 6,000 we get the 1,000. Okay, that is out of 6,000, 5,000 times we will get 3, and 1,000 time will get 6. Okay, and so we can find the average now. So 5,000 times will get 3, plus 1,000 time will get 6, and it is divided by 6,000. Okay, it is divided by 6,000. Okay, so this is the total number of trials. Okay, which is nothing but 5 by 6 into 3. Okay, see here 5 by 6 what we have estimated roughly. Okay, 5 by 6 into the actual value that we are going to get. Okay, which is 3, and then 1 by 6 times will get 6. Okay, and if you add, we'll get 3.5. Okay, so we need not actually roll the die for 6,000 times to compute this 3.5. Okay, so that is the beauty of the distribution. Okay, So let's try another one. We have a standard die. Okay, we are trying to roll two standard dice. Okay, that means that each side has a different value. Okay, you will win $100 if the sum is 2, and we will lose 100. We win $1,000 if the sum is 2, and we lose $100 otherwise. How much do you expect to win per trial? Okay, and what is the probability that the sum of two dice will be 1 by 36, right? Both the dice should turn to 1 and 1, then only we'll get the sum to be 2. Okay, and we know that the toy experiment, okay, has 36 some outcome. So the probability that the sum of the dice is 2 is 1 by 36. Okay, and again we are considering only two things. Okay, the success and the failure. If we win, it is success, otherwise it is failure. Okay, so this is P, and 1 minus P will be apply the Bernoulli distribution. Okay, so 1 minus P will be the probability of the failure, which is 35 by 36. Now assume n trials, okay, because you want to find the average. Okay, so you have, this is the value you will win, right? It is like the value that, I mean, it is more like the value that appear on the, I mean, in the previous example, it is more like the value that appears on the die. Okay, but here okay, so we have 1000 into n by 36 because we are making n trials minus 100 into 35 into n divided by, so this is what we lose. Okay, that's why we make a subtraction. Okay, yeah, this one. Okay, so now what is the expected average per trial? Again, I have to divide this by n, so these both the n's will be negative number. Okay, so anyone, will you attempt to play this game? Yes or no? Am I still connected?